like to thank you all for attending. I'm your moderator, Luke Antonio, editor of Intelligent Transport. Today's speakers will be Yovav Meydad, Chief Growth and Marketing Officer at Moovit, and Ben Galon, PhD, Head of Data Scientist Team at Moovit. Today, their presentation will be followed by a live question and answer session where you can ask questions about what you've heard. You can submit questions at any point during the webinar using the questions panel situated in the menu on the right. That's all from me for now, so allow me to hand over to today's keynote speakers, Yovav and Ben. Over to you guys.
Thank you, Luke, and hello everyone on this webinar today. It's a pleasure to have you all here. Today we're going to talk about how we use data analytics to optimize on-demand transport. But I want to first start by sharing with you, to those of you who are not familiar with Moovit yet, give you a little bit background about our company and our journey so far. We started Moovit over 7 years ago, and our mission from the get-go was to simplify urban mobility all around the world. And initially, we focused on creating a product for consumers, and the citizens who live in different cities benefit from the simplest and most intuitive mobility experience in the world. It's available on Android, iOS, and the web, and it combines all the information about transit, micromobility options like bicycles, scooters, ride-hailing, and others, including real-time information, service alerts, plus crowdsourced data, which is our secret sauce. And using Moovit, a citizen basically has everything he needs in order to travel around the metropolitan area where he lives or works in a most convenient way. And the functionality that he gets would be trip planning, real-time arrivals, payment integration where it's available, and other mobility options. In those 7 years, we've grown to have more than 550 million users using Moovit on any of these platforms, web, iOS, and Android. The product is free to download. And we, because of the usefulness and the fact that we have a lot of users recommending the service to others, we're growing now at a pace of more than 1.2 million new users every day. And luckily, we do it without spending anything on marketing. The reason we get so many users and our growth is so global is primarily because of the fact that we have users in so many locations, and I'll talk about it in a second. The users that we have today that use our service, also by the fact that they're using Moovit, we collect over 5 billion data points every day and add them to a large repository of people movement data that today is the largest in the world. I want to emphasize that all of this information is aggregated and anonymous. Moovit does not collect any personal data from users. We don't have email addresses or ask for names. And we are GDPR compliant. I mentioned about the fact that we have 550 million users and growing at a pace of 1.2 million users every day. And it's greatly attributed to our geo expansion, to the fact that we provide our service in over 3,000 cities across 92 countries. And this way, we've built the largest repository in the world of transit data, and it's also the most accurate one. We have information of over 7,000 transit operators, including their full entire fleet of lines, stops, and schedules. We connect to thousands of service alert feeds around the world, real-time information. And in the past 2 years, we've also invested significantly in an infrastructure to connect micromobility services. And today we have more than 300,000 vehicles of different forms in our database. The reason I'm said that our transit data repository is the most accurate one is greatly attributed to a large community of volunteers that we have built along the years. And we call them the Mooviters community, and they are responsible to map and edit transit information in different cities around the world where this information is not available in a digital format by transit agencies. Today, 60 to 70% of the cities we have launched service in Moovit were completely mapped by our community. This is something that we're very proud of, a community that we care a lot of, because they are creating a huge differentiator for us in the quality of our data and its coverage. And some, by the way, call it the Wikipedia of public transit, if you want to kind of understand how it looks like. Another thing that I'm very proud of is the fact that Moovit is considered today as a leader when it comes to accessible mobility. We offer capabilities for users with different forms of disabilities that allows them to travel independently around their cities. And those includes features for visual impaired and blind users, like complete voiceover and talkback support. These are screen reading technologies that smartphone have. For users with hand motor impairments, we optimize the user interface with large buttons and large hit targets. And for users with ambulatory impairments, we developed capabilities into our multimodal trip planners that allows them to travel in a wheelchair and never come across a staircase. And some of our partnerships in that area include ONSE, Be My Eyes, and others. But during these 7 years, we didn't stop as just being a transit app. And this is something very important to emphasize. A lot of people still might think and know us as a transit app, but we are much bigger than a transit app. Using the same brain that powers the Moovit consumer app, we have created 2 additional solutions that leverage these assets that we have created. Our multimodal trip planner, which is the powerful in the world, at least to what we consider the largest and most accurate transit data repository, and the largest people movement data repository. These are the 3 unique assets of our brain, and what they allow us to build 2 solutions, one for cities and transit agencies, and one for large businesses. Let's take a closer look at both segments, which will lead us to the detailed topic about on-demand today. So for businesses, we have created APIs that gives them access to all of the capabilities that power Moovit, trip planning, near-time arrivals, and more. Some of the customers that already leverage these capabilities, our transit APIs, include TomTom, Microsoft, Lyft, and Uber. I'll give you an example to how Uber uses our APIs. They have recently added public transit information into their app, and that's available in 5 cities and more to come. And the entire experience of showing Uber users transit routes, live arrivals, itineraries, etc., is fully powered using the Moovit transit APIs. Lyft is also using Moovit now to power nearby arrivals and real-time information about transit. You can find it in New York City. That was launched just a few weeks ago. So these are 2 examples how large businesses use Moovit transit APIs. When it comes to cities and transit agencies, we've developed a mobility as a service platform for those organizations that is helping them increase ridership and customer satisfaction using a set of components that power their mass offering. And here are just a few of the cities and transit agencies from all parts of the world that are using our mass platform. And as you can see, we have here cities from North America, Asia, Europe, and others. And these are some of the customers we're very proud of. So what is it that we offer as part of our mass platform? What we understood along the years is that each city has a different need when it comes to mobility or mobility as a service adoption in general. And because of that, we've created a modular platform that has a number of components, and each city can choose which option to use. One of them can be a white label app, or white label app integrated with mobile ticketing in case mobile ticketing is available in the city. Our unique urban mobility analytics that is a product delivering insights about where, when, and how people travel around the city. An on-demand solution for planning and operation of a fleet. And for transit agencies that don't have real time and are looking for a cost-effective solution instead of expensive AVL, we have a product called Moovit Time Pro. And that was kind of an introduction to Moovit, just to have everybody on the same page. I want to now open it for a short poll that we're really interested to know. How did you get to work today? So please use your mouse to make your selection, and then click submit located at the bottom of the screen. We'll give you a few more seconds to submit your answer. And now, after this poll, and you submit your answer, I'm going to turn it over to Ben to continue and talk in much more details about our on-demand solution.
Thank you, Yovav. Looking at your response, we can definitely see that most of you are private cars users, and you're doing your daily commute by using a car. In the presentation, we're going to address this and see how we can convert daily car commuters to use public transit. So in this part, we're going to do the following. First, we will set our definition of on-demand service. Then we will explain where it's fit in the jungle of mobility services. And at the end, we will see a bit about the planning process and review Moovit's unique solution to the on-demand challenges. So let's start by defining on-demand service. What is on-demand service? Let's take a look on the range of the available mobility service. On the one side, we have the mass transportation solution. We can take the bus for an example. And on the other side, we have the taxi. The bus is designed to be low-budget solution for the crowd, and therefore take many passengers along a fixed route. This means a lot of waste of time for one specific passenger due to long deviation from its direct trip. And of course, it also means a long waiting time. The taxi is an exclusive service that takes at maximum full-hand passengers directly from their origin to their destination, and accordingly is usually expensive comparing to the bus. We can define on-demand service as services in between this range, between the taxi and the bus, that answer the following criteria. First, it's on call, meaning it can be called by an application or by using your phone. Second, it's have a dynamic route, not a fixed route. And third, it must be shared by more than one passenger. Now let's examine 3 cases where an on-demand service can be beneficial. To understand the first case, some background on how transit systems are designed is required. Usually, the transportation system designed is based on a mass transportation network, such as a subway, light rail, or even heavy rails. We illustrate this by using a schematic diagram in which the black line describes the mass transit network, the white dot shows the station in the system. The access to the mass transit stops is usually made by foot. The area that can be accessed by walk is shown in dark blue area on the diagram. Those systems tend to be more dense in the urban areas, but sparse in the suburban area. As you can see, there is still holes that are not connected to the system. In traditional system designs, the way to bring passenger to and from the mass system is by feeder lines. Those are bus lines, usually similar to local lines, with many stops along the way. And they have a long way arriving to the mass transportation network. The area covered by those lines is marked in blue. The problem with the feeder line is that they are usually very inefficient, and users find themselves spending more time in the feeder lines than in the mass transportation network. This might have been good enough centuries ago, but passengers today are not satisfied and demand more efficient service. This leads us to the rise of the micromobility services. Micromobility services are services such as dockless bike and scooter, which are replacing the feeder lines in the dense urban areas. Those services range is shown in the green area at the diagram. Due to limitation in expanding the micromobility service, there are still areas where passengers are outside the center of the city, left with the old feeder lines. This is the place where on-demand service can be used and replace some of the feeder lines with an on-demand service. The on-demand service will bring passengers to the mass transit network in more comfortable and efficient way. Let's take a look at the second possible purpose of on-demand service. And this purpose is to replace a local line. In the screen, you can see a screenshot of line 402 in Tyson's area. We will discuss this area soon. Those lines, the local lines, by design, have many stops with only few passengers at each one. In addition, those lines tend to have many detours to pick up passengers from within the neighborhoods. Those features make local lines very inefficient to passengers. Replacing those lines with on-demand service will allow passengers more direct ride at their convenience time. Of course, that not every single local bus line needs to be replaced by on-demand service. It depends on the line shape, on the line frequency, and on the line utilization. We want to replace inefficient local lines with dynamic and adaptable service. In those cases, we might consider to allow pre-orders, orders that are going to be to future time on the on-demand service, to allow passengers better planning of their day. The third case where on-demand service can be beneficial is to reduce vehicles in city centers and dense urban areas. Recent research showed that hailing services are contributing to the congestion and do not assist to reduce traffic. The main reason is that those services are not shared and served most of the time only one passenger. In addition, those vehicles are on the road even when there are no passengers on board. On-demand service, on the other hand, is shared. One on-demand vehicle can replace 2 to 5 conventional taxis with minimum inconvenience to the passengers. This kind of implementation might require price regulation or any other external interference in the mobility market, since individual users will prefer their own benefits on the entire group benefits. This leads us to a review of the different players and their entrance on the on-demand solution playgrounds. First, let's take a look at the rider. The rider will usually look for a fast and comfortable ride from their origin to their destination. It should be shared with few many passengers as possible, should be shorter waiting time, minimum ride deviation, less walking, and of course, the lowest price as possible. On the other hand, we have the operators. The operators want to increase its earning, which means less driving kilometer and fill as much seat as possible, or in other words, sell more tickets. The third and less obvious player are the cities and the municipalities. They represent the entire population well-being and aiming to reduce congestion, reduce air pollution, and save time for the benefits of the global economy. The key in a successful planning of on-demand service is finding the right balance between those three players. Of course, that the point of balance, we call it the golden point of balance, is not the same for different locations. In any location and any service area, we will need to find the golden point of balance in the different characteristics and unique features of the specific chosen location. The point of balance is also depend on the service goal. Sometimes we will use on-demand to replace line with bad service, and sometimes we will want to use on-demand to reduce the amount of cars. It means that we're going to have a different goal for each service and each location. Moovit's unique approach to a successful on-demand solution includes two aspects, planning and operation. In the following slide, we will demonstrate the importance of planning phase before the implementation of on-demand service solution. Introducing planning before implementation of the on-demand solution can differentiate between successful and failed projects. During the operation, more valuable data is gathered. We can use this data in order to improve the planning and then improve the operation, and so on. The planning process aims to answer the following questions. Is on-demand service the right solution? Is there a point of balance between the players where everybody wins and the service can exist? Second is how many vehicles are required along the day. The amount of required vehicle can, of course, be changed over the time. Third, we will try to address the question is the amount of seats in each vehicle. Does 5-seat vehicle will provide better service than 10 or 15 seats vehicle? And at the end, we will try to address the question, what are the desired service area? Before we dive into the example of analysis process, let me introduce the tools that we are using. The two main tools used for the planning are the urban mobility analytics that we use by data that collected from Moovit users and other resources to analyze by special tools that was developed here at Moovit. And the second is dedicated simulator for on-demand solutions. We are required to use here a simulations since the data is complex and have a lot of interconnection that can influence, and therefore the data cannot be analyzed by a usual or standard analytics tool. Please allow me one more slide before the planning process. Let's take a minute to familiarize ourselves with the terminology and definition of on-demand service. Like any transportation system, we have two opposite sides, supply and demand. In on-demand system, the supply is the available vehicles and the demand is orders in the service. Our analysis does not look at the demand system as a separate and disconnected system. It's look on the demand service as a part of the entire mobility ecosystem. So when discussing the demand, we're also considering multimodal journeys and conversion between mobility modes when a service will be introduced, meaning that users that usually use car, like most of this user in this webinar, can convert it and start using on-demand service together with public transit. The simulation can be fed with different order scenarios according to the above. At last, let's take a look at the planning example. In this example, we will illustrate the challenges in the planning and the deployment of on-demand system. In this example, we will take a look at Tayson Center area, which is located at Fairfax County at Virginia, US. This area is about 8 kilometers or 10 miles west to Washington, DC. The polygon on the map shows the desired service area. This analysis was prepared by the data science team here at Moovit, especially by Michael Sharney and Simon Cornice. Let's try to understand the main problem in the desired service area. This is a screenshot from Google Maps that shows the typical traffic in and around Tayson's Corner Center. The time is the highest peak in the week, Monday at 8 a.m., we can see that the roads and the junction lead to Tyson centers have slow and very heavy traffic. This traffic is around 10 a.m. One solution will be to add more lanes and build new roads to address the congestion at the peak times. But we would like to test if offering on-demand service can ease the traffic in the peak time. So the main goal of service will be to reduce congestion by reducing the amount of car and not by building new lanes and roads. Next, let's take a look at the status of the public transportation in the area. The public transit has two main components, the subway and the bus networks. Most of the lines in the area are either local lines or feeder lines. Sometimes the same line can be used for both purposes, be a feeder line and the local line at the same time. Let's take a look at the subway network. It's based on the Metro Silver line and the Metro Orange line that connect this area to Washington, D.C. We can see the two branches of the metro system on the map, marked by orange lines, and the subway stations are marked as diamonds. The subway seems to fit well to the main employment and commercial areas, but the bus stops are very sparse and widely spread and located only on the main roads. And we can easily identify that entire neighborhoods are connected from the public transit grid. Even without looking to the schedule, this can be an indicator to a low level of service in this area. This is due to low availability to the bus stops. After understanding the surrounding, we will start investigating the mobility patterns in the area. While doing so, we will collect our findings that's going to be useful to lead us to interesting conclusions and insights. The data in the following slides were gathered by using Moovit Urban Mobility Analytics Systems. We will start by looking at the pattern along the day. In the chart, we can see that the amount of daily trips by day that divided to 4 categories. The number on the y-axis are daily average for a typical working days. And the categories are entry category, marked by blue. Those are trips that originated outside the service area and their destination is inside the service area. The exit category are the opposite. Those are trips that start inside the area and their destination is outside the area. Then we have the internal trips. Those are trips that start and end inside the service area. And at the end, we have the external. Those are passengers that only pass through this area. Their origin and destination is outside the area. We can see that most of the trips are entering or exiting trips. And in the morning, more passengers are entering the area and presumably leaving the area at the afternoon. We can conclude by saying that 82% of the passengers are cross-polygon passengers, either entering or leaving the area. Next, let's take a look at the mode split. The table in the slide shows us the mode split in the morning for each one of the categories mentioned above. We can see that the car is the most common mode across all categories and especially for the entry and exit passengers. Let's add this to our finding. Now, it's the time to test our assumption from previous slides and see where are the main attraction points in the area. The heat map shows that all journeys origin and destination in the morning peak. We can identify 3 main attraction points. The first, in the center of the screen, is Tyson's Commercial and Business Center. This can be identified as the main attraction area. The second, located at the bottom left side of the screen, is the attraction point that represents Merrifield. And the soft attraction point is George Mason University. The university have their own shuttle service, so we will ignore them for the continuance of this analysis. Since heat map are only give us the impression of the situation, to get more accurate result, we are using actually a measurement of the origin destination matrix that is based on polygons. If you remember, the subway map shows us the exact same attraction points, and they have high correlation between those attraction points and the subway stops. But if the subway networks lead us to the main attraction, we have to ask the question, why the subway use is so low? To try and answer this, let's take a look at the commute time between two popular polygons in the area. The origin will be a neighborhood within Arlington, directly surrounding the subway stations, and the destination will be Tyson Center. The polygons are shown on the map in blue. We will look at the distribution of the commute time in the morning peak. We are looking at the distribution since there are many rides from different locations within those two polygons. As the tables clearly indicate, the driving time is very similar to the subway time. And the median even shows us that the subway is faster in 5 minutes than the driving time. This increase and not provide any answer to our question from before. Why is the subway use is slow? Let's take a look at another heat map. This heat map shows us the subway station catchment area. This area is the origin and destination of journeys that their main mode was subway. We can see that those users are using the subway station is similar to the origin destination as the entire population. This leads us to the preliminary assumptions that the low usage in the subway is due to the accessibility to the station. It is difficult to get to or from the stations, and this is why people are avoiding using the subway network. I'm sorry, but this slide should be a lot farther, so we probably have some kind of a problem here in the presentation. I think I'm going to address these slides right now since it's an interesting slide, but you will excuse me about the assumptions that we did before about the land use. So we will usually start the analysis by looking at the land use. In this case, we're going to complete the analysis by looking at the land use. But this slide shows us the data that was collected from Fairfax County GIS. You can see the green areas that are showing the open lands, park, and architectural. And you can see the blue areas that mark residential areas. And the red indicates industrial, office, and commercial use. So from a quick glance, we can see that most of the area is suburban, marked by low and medium density of residential use. And there are two main employment and commercial centers. The largest is Tyson Centers, and the other is Merrifield. Of course, we already identified this by using our data. So in this case, we can see high correlation between our data and the land use area. We can assume that this will be the major attraction, and we already proven that these are the two main attraction points in the area. So a quick reminder where we have been before the slide that jump in previously. So we had the assumption that people are avoiding the subway network due to a long or inconvenience first and last mile. So instead of show the full proof for this assumption, and we have the full proof for this assumption, we will settle for a simple example. We did a triplan in Moovit web application from typical ride between the two polygons that was shown previously. So the first suggestion that come into the triplan is a combination of walking and subway. Let's examine the times on this route. So firstly, we have a walking leg that take 9 minutes, then we have a subway leg that take 18 minutes, and at the last, we have a walking legs that take another 7 minutes. In total, we have 18 minutes in the subway and 16 minutes by walking, meaning that we spend almost the same time by arriving to the station as the time spent on the train. Bear in mind that in this case, there is no reasonable alternative for walking, no feeder lines, and there are no micro-mobility there. So this example supports our assumption that the main problem is the station accessibility, meaning first and last mile issue. So what did we did so far? We gathered findings that led us to the assumption that there is a first last mile problem here, and this gave us the goal for this, or the service target. And the service target will be to improve the first last mile experience. We're doing so to increase subway use by converting car riders. This is done in order to reduce traffic around stations. This is the time to use the second tool we would like to use. This is the simulation tool. We have run many simulations with different service parameters. In this case, we will focus on one simulation with 30 vehicles and 50 hundreds orders. The order set was built based on our targets and take into consideration the expected conversion from car to public transit. What we can see in the screenshot is the Moovit back office application. This application, with some adaptations, is also assist us to investigate a specific simulation. In the screen, we can see the main performance measurements, which are acceptance rate, wait time, onboard passengers, or number of pickups, deviation from a direct ride per passenger. When testing the simulation results, most of the measurements came up right fine, as expected, but one important measurement raised some concerns. This measurement is the predicted wait time. The wait time have high influence on conversion of car riders. Long wait times mean the car owner will continue using their car and not transfer to use on-demand service and public transit as we desired. The chart in the slide shows the distribution of wait time. The upper chart shows the predicted wait time at the morning peak, and the lower slide shows the distribution through all day. In the morning, the simulation predicts that the wait time will be between 4 to 14 minutes, and the entire day it's predict 5 to 19 minutes. Those numbers might be a bit too high for converting passengers. Let's try to understand why the wait time is so long. The following is some kind of thumb rule that can provide basic explanations for the low performance. In on-demand transportation, the resources are the vehicle. The number of vehicles in the area determines the available supply, which have straight influence on the level of service. Inefficient distribution of vehicles leads to low supply in high demand area and therefore long waiting time. According to this, the solution is obvious. Let's just add more vehicles. This will result in a lower waiting time. The riders and the cities might be happy with this solution, but the operator will not. More vehicles mean higher operational cost. So we will need to find another way to reduce the wait time. This may make us to try to consider tackling the problem from the distribution perspective. Let's try to understand the influence of the vehicle distribution. In this snapshot of one simulation run, we can see that the vehicle, the gray dots in the service area, are spread all over the area. In specific, we can see one order that is crossing the service polygon. We can see the orange point, this is the origin of the user, and the purple point, this is the destination, and we can see the vehicle marked in green. The main problem we detect here is that we cannot control the supply distribution within the area, and therefore several peripheral requests can deviate the supply from our strategic area. In this case, is Tyson Center. To address this, Moovit have developed the corridor methodology. The main idea behind the corridor methodology is to split the service area to corridors and assign vehicle to each corridor according to 1, the expected demand of the corridor, and 2, the service target. The deviation to corridors The deviation to corridors and the distribution of vehicle between the corridors will aim to increase supply in high demand and strategic area. Two more points worth mentioning are that the corridors may be dynamic and change along the day. In addition, the distribution of vehicle between the corridors can be changed throughout the day. The other point that's worth mentioning is that assignments of vehicle is not strict. In case of needs, vehicle can be reassigned in real time. Let's look at the suggested corridor for this specific service area. First, we will have corridor number 1. This is the main service area. This is the corridor that's surrounding the higher attraction point in the area, and this is the highly strategic since we would like to achieve high conversion rate in this area. This corridor expected order is about 23% of the entire orders. Then we have corridor 2 and 3. Those aim to serve local arriving or departing Taysons. Those corridors expected to have 44% of the orders. Finally, we have corridor number 4, which will take orders that do not fit in any other corridors. Distribution of the vehicles between the corridors is made according to the expected demand shown here. After defining the corridors, we have run some more simulation with the same amount of vehicles and the same order sets as before. The only difference is the corridors and the difference between the areas. On this slide, we can definitely see that more vehicles are found themselves in the center area of Tayson centers. Let's examine the results of the simulation and how it's influenced the waiting time. So in the updated charts, we can see the results of the single service area in the green bar. This is what's shown in the previous result. The red bar showed the expected waiting time for corridor 1, which is the most important corridor according to our definition. We can see high improvements. Now, with the expected wait time are 1 to 5 minutes. Corridor 2 and 3, marked in purple and cyan, also show slightly improvements. But since we didn't add any more vehicles, the improvements in corridor 1 to 3 must take its price. And in this case, it's going to be longer waiting time in corridor 4, marked in the orange bar. We can definitely say that in this case, the corridor methodology has solved the problem and allow better performance to the majority of the passenger, especially in the strategic areas, without adding any more vehicles. Look like we find the golden point of balance between the players in this case. To conclude the planning phase, we explain what is on-demand service and where it can fit in the fabric of urban mobility. We demonstrate by example the high value of planning based on rich data and how it can differentiate between successful and failure implementation. And we introduced Moovit corridors methodology that aim to solve the imbalance supply problem.
Thank you, Ben, for explaining Moovit's unique approach to on-demand planning using people's movement data and the proprietary tools that we built in Moovit to power them. The second phase of our on-demand solution, as Ben said earlier, is operations. And for that, we created all the components an on-demand operator needs: a driver application, an app for the riders, and a back office for the operation center. Let's take a look at them one by one. The rider app is Moovit. And sorry, let's make sure that the video plays. Yes, perfect. So the rider app is Moovit, or a white label version of Moovit in case a city or a customer is interested in such a white label dedicated app. And the first thing to highlight about our rider app is the fact that on-demand routes are calculated by Moovit Multimodal Trip Planner, meaning These are routes that combine public transit with micromobility options, bicycle, scooters, walking, ride-hailing, and on-demand routes, or any combination of them. And within our product, they are displayed to riders one next to the other. And using this multimodal approach, riders can see and compare all of their options and choose the one that works best for them. And using the app, they can reserve their seat, pay for the ride, and then get notified when it's time to leave towards the pickup point and view it in real time as the on-demand shuttle approaches them. The second component within our on-demand solution is a back office for the operator's control center. It's a web-based tool that runs in a standard browser, web browser, and it doesn't require installation of any custom hardware on-premise. The tool provides the operator staff a comprehensive overview of their entire fleet, including different level of service reports to achieve maximum operational efficiency. It also includes capabilities such as route planning, dispatching, messaging with drivers, reports, and customer support elements. The third component in our on-demand solution is a driver application. It's an app that's running on any standard Android smartphone or tablet, and which makes it easy to deploy, maintain, and also onboard new drivers and get them trained. The app provides drivers with turn-by-turn instructions to pickup points and drop-off stops, and it allows drivers to identify the passenger when they go on their vehicle, indicate a pickup event or a no-show event, and also to send messages and communicate with the control center. So I want to summarize what we covered in today's webinar before we open to questions. So we defined what on-demand means and what are the specific use cases it's relevant for. We demonstrated how a planning phase powered by urban mobility analytics, data science, and simulation is critical before operating an on-demand solution, since it helps you define the right areas where the solution should operate, and by that optimize service. And we showed the Moovit operational components that power an on-demand fleet. And finally, I want to emphasize that we at Moovit view on-demand as one component within a bigger puzzle of a mobility ecosystem. And that's why our on-demand solution is one of the 5 components within our mobility as a service platform, and each of the other components connects with it. So our urban mobility data feeds the on-demand planning phase, and on-demand operation connects with the white label app in order to perform the booking process. I invite you to visit our website to learn more about our MaaS solutions, and also you can there request a demo of our products, and we're happy to take any questions now.
Brilliant, Ben. Thank you so much for your presentation, and thanks as well to Yovav. There's a lot of great insight here for us to unpack. So in a moment we'll begin the Q&A session, but just a quick note to our listeners that you can still submit questions using the questions panel in the menu on the right hand side. But with that aside, let's start the Q&A. So the first question is regarding sample sizes and how to expand population to get the right amount of trips. I'm not sure which one of you would like to take that question.
I will take this question.
Ben.
Yeah. Thank you. So this is an excellent question. So first, I will need to take a minute to explain the problem, because some of you are not familiar with this problem. So the question is sample size, how to expand population and get the right amount of trips. So in statistics, the main problem is how we take a sample size and projected to the entire population. The usual way to address this problem is by using a random sample. But since we are using data that collected from mobile users and other signals, the data will be biased by definition, since we cannot collect a random sample. So our answer to this is developing a unique model of calibration. The model of calibration takes external data sources, such as demographic data or census data, and external transportation information, such as traffic count and ticketing information. This model is actually find two main biases factor and fix them. The one based on the user segmentation, the user geographical segmentation actually, such as user home, location, work location, etc. And the other is based on the transportation mode that was done by each user. So applying this model to our sample provide us with represented data that can be used to represent the entire population.
Next question.
Yeah, brilliant. Thank you very much. So the next question we have here is about personal data, and it's obviously there are growing concerns about the collection, storage, and usage of personal data. So how do you find the right balance between benefits and privacy?
So thank you. This is also a very good question. And the answer is that we actually found a way to enjoy two worlds, and we do not need to balance between the privacy and enjoying the data. And I will explain. So as mentioned before, our application and data is fully GDPR compliant. We take the privacy of the users very seriously. So first of all, the data that we provide to our customer will always be aggregated, meaning that it will present statistical measurements such as count, averages, etc., for only large amount of users, never for a specific or small amount of users. In addition, the data will always be after calibration. I just explained the calibration method, and therefore there is no way to reduce it back to the sample size. So this means that the data we supplied will be always anonymized, and there is no way to track back any individual users. We also make sure that during the data collection pipeline, we will remove any unique identifier along the way, in addition to the user identity that is actually scrambling at the beginning of the data collection process. So according to this, you can understand that we find a way to enjoy the data benefits without damaging the user privacy. We're ready for the next one?
Yeah, absolutely. While we track down the next question, let me just leave you with this one. So how would you recommend starting an on-demand shuttle project in a town, say with a population of about 25,000 people, that would improve the existing public transportation network?
Okay, so we actually showed this in the presentation, but I will give a bit more elaboration about this. So as we see this, the deployment process should be start by doing a large analysis on the city. We will need to try to identify where on-demand service can be beneficial to the city itself. After we've done this analysis and find the right places to deploy the service, then we will recommend to starting a pilot phase. In the pilot phase, we will actually gather more data that could validate and improve our planning. So as a result, we will get a much more bulletproof planning. And after we improve the planning, we can get back and continue the deployment stage. We also recommend about gradual deployment stage, so we can do it all the time, gather data, get back to the planning, and continue with deployment.
Brilliant, thank you very much. Thanks a lot for elaborating on that one. So we have another question here. So the question asker would like to know, So you've said during your presentation that on-demand will reduce the number of vehicles and thus reduce congestion. But there are multiple recent studies that actually claim the opposite, that cars stay the same and the number of kilometers driven goes up, which actually increases traffic. Could you clarify that, expand?
So you're correct. I actually addressed those researchers in the presentation. So basically what the on-demand service could do, we could take one large car and make it share between several people. So those researchers, and I hope we are addressing the same research, actually indicate that deploying many small vehicles in an urban area will create more congestion. What that we are suggesting is deploying large area that's going to be more shared. And as I said at the presentation, in such cases, we actually might need the municipality interference in order to make sure that the deployment will be successful. Sometimes we would like to regulate the prices, and sometimes we would like to avoid small cars to be on the streets. And we actually start seeing something like this happening. Yesterday, I noticed a publication from New York City Town Hall that addressing this point, that they are going to start regulating regular ride-hailing services and the prices there.
And it's also important to emphasize, as been presented earlier, the difference between on-demand services that are operated by private cars, by companies like Uber, Lyft, and others, and on-demand services powered by a shuttle van that can occupy 8, 10, 12 passengers. And the model that we presented today and the simulation recommends those type of vehicles.
Brilliant. Thank you both very much for input there. Wary that we are beginning to run short on time, we have a question here. Obviously, you know, the rural environments are as important for mobility as urban. So in rural areas, the supply of public transport will diminish and, in fact, is diminishing. So how can carpool and shared mobility offer affordable solutions?
So I think we touched on it also during this example. In rural areas where today there are local lines that are very inefficient, and for that reason, passenger or the citizens choose to avoid them because it's not fun to ride a line that stops in 30 or 40 different stops. The availability of on-demand services as a way to get to the transportation hubs, to those subway or train stations, would be the place for on-demand mobility. Now we're talking about trips that are fairly short in their distance, not trips that require a passenger to travel long distance into the city. So we definitely see on-demand as a way to address the first mile, last mile problem, especially in rural areas. But then the passenger will continue his trip into his final destination using public transportation.
Brilliant. Thank you very much. I think we have time for just one more question before we close up the session. So does Moovit offer an open API for transit operators that they can use on their own website to offer route planning for their own travelers?
So we have partnered with many transit agencies around the world and provide them with web-based trip planners and web-based apps that can be embedded on the transit agency's websites. They are in different sizes, widgets, etc. And many transit agencies choose to use our free web tools because it saves them, the cost and the labor or manpower to develop their own solution. Any transit agency representative on the line is encouraged to get in touch with us. We'll be happy to partner with you. These are free embeddable web apps that we give for free, and we see great adoption of them.
Brilliant. Thank you so much. Unfortunately, that is just about all we have time for today. Any unanswered questions, and there are quite a few, will be responded to via email. So my thanks to both Ben and Yovav for their time and their insights today. It's been absolutely fantastic having you both with us. So as you leave the webinar today, a survey will appear on your screen asking you to rate today's webinar. If you could just take a moment to provide us with your feedback, that'd be fantastic. If now isn't a good time, then the survey will be sent to you shortly via email. If you can complete it when you can, we'd really, really appreciate it. But for now, on behalf of Intelligent Transport and Moovit, I'd like to thank everybody for attending today's webinar, and we hope to see you all again soon. Thank you very much.
Thank you, everyone.